Okay, thank you, Diego, for the introduction. And also I would like to thank Edgar and Damien for the invitation for this nice section. Okay, so what I'm going to present is it's a joint work with Felipe Chavez Silva from UFPB and Sylvain Verdosa from Université de Tours. And I will present some part of this paper accepted in the SciComm this year. Okay. So my talk is divided in three parts. I will start with an introduction of control theory, and also I will present what I mean by switching controls. Then I will present our main result, and I will finish the talk with some conclusion, comments, and presenting some open problems. Okay, so a control system is a dynamical system which involves two variables. One we call state, and the other one we call the control. So the control here in this system is the variable u, and the state is the variable y, which is the solution of this dynamical system. So the goal, and u here can be chosen freely in such a way the solution of this system behaves in an appropriate manner at the final time. Okay. So in particular, when we are talking about controllability problems, we have these three definitions of controllability problems. We are talking about exact controllability at time t, when for any initial data u0 and any target ut at your space S, you always can find a control u in some appropriate space C, such that the solution of this dynamical system can be steered to YT, to the target at the final time. You have two particular cases of exact controllability. We call no controllability at time t, when your target is zero, is the equilibrium. And we are talking about exact controllability to trajectories when your target ut is the final data of a particular solution of this system. Okay, and another definition of controllability is approximate controllability at time t, and in this case is a weaker property than exact controllability, and it means that for any initial data and any target and any neighborhood of the target, you always can find a control u such that your solution enter in this neighborhood of your target. Okay, so we have four definitions of four concepts of controllability: exact controllability, no controllability, exact controllability to trajectories, and approximate controllability. And these are qualitative properties of a dynamical system. So Well, it's not easy to prove this qualitative property. So there is a classical duality way to see these qualitative properties in terms of some quantitative properties. So but before that, I will just show an example, practical example, in which you can interpret it as a control problem. Here is an Roman aqueduct. It's located in Segovia, is the city where I am right now. And here is a kind of bridge in which the Roman used in order to driven water from the mountains that you see here to the city, okay, and the bridge has some inclination in order to control the flux of water, okay, in order to arrive to the city in an appropriate way with an appropriate velocity, okay, to some tanks or other place in the city. Okay, so let's show now the duality that allow us to see this qualitative property as a quantitative properties. Okay, so we will consider here a linear problem, okay, and we will play a little bit with functional analysis. So associate to this system, in particular to these two operators, we have the operator A, okay, which is the operator of the equation. This operator can be a partial differential operator, can be a matrix, whatever you want. And B is another operator which will tell us how the control acts on the system. Okay, so we define two functionals. Okay, the function f is a linear operator which associates to any control to the solution at the final time. Okay, is starting from zero. And the operator G is another linear operator which maps the initial condition to final state of the solution associated with zero control. Okay, so you can compute the adjoint of these operators, and here you have. So f star of zt is b star of z, where z is the solution of what we call adjoint system. And g star of zt is z at zero. Okay, so the exact controllability, one can easily see that is equivalent to the surjectivity of the functional f, and the functional f is onto if only if the adjoint system satisfies this condition. Okay, and the approximate controllability is equivalent to the density of the range of f in the space S, and this is equivalent to the injectivity of the adjoint of f. And this is not. I mean, these two properties. It's we teach in the functional analysis course, but this is a little bit new for people that have studied functional analysis. And the exact controllability is equivalent to this inclusion between the range of G and F. Okay, and this can be proved that this is equivalent to this property relating the adjoint of G and F. Okay, and these properties, what I'm showing here, is presented in a paper by Doletsky and Devido in the, let me show here. So, oh, yes. In a paper in Psychon in 77. Okay, and since we are in the linear case, the exact controllability and the null controllability are equivalent. And this is, I will not say anything else because this is a little bit classical. Okay, so on the sample is the heat equation. In the heat equation, you have, here you have the control acting in the distributed case. So you control act on a small part of your physical domain. And here you have the control acting on the boundary, on an arbitrarily small part of your boundary. So the solution of the heat equation, everyone know that the solution is, we have the regularized effect, which means that outside O, the solution of this system, if the initial condition is L2, for instance, or H minus 1.
Excuse me, Diego. I don't see the heat equation. Did you switch slides?
Yes. Can you see now?
Can anyone else can see it? I don't see it.
Oh,
it's frozen for me.
Now?
Yeah, now it is. Yeah. Cool.
Okay.
Yes.
Sorry. So we have here the heat equation, and here what I was saying, that the control is acting in a small part of your domain, and here the control is acting in a small part of your boundary. And since outside O, for any initial condition, the solution is say infinity outside O because of the local parabolic regularity of the heat equation, since you have here a constant coefficient. So we have that outside O, the solution is say infinity, okay? And this implies that I will never obtain the exact controllability for this system because I cannot driven an L2 initial condition to another L2 initial condition. Okay, so what we can prove in this case is the no controllability, which I wrote here, and the no controllability is equivalent to the observability inequality. This is the observability inequality obtained from the previous slide in the distributed case, and this is the observability inequality or weak observability inequality in the boundary case. And this is some reference. The result for the heat equation was first proved by Devido by using the moment method. It was proved just in the 1D case, and almost 20 years later, Lebeau and Robiano extended, and Fuzikov and Manovilov, they prove the result in the general case, in n-dimensional case. Okay, so switching controls. So I will call again this linear system by CP. Okay, control problem. Okay, and the space where the solution belongs, I will call H. Okay. And now the operator A is such that minus A is generate a C0 semigroup. Okay. Okay, and I will assume that the operator B, which tell us how the control acts on the system, is a bounded operator from U to H. Okay, and the control U we will search it in L2 with values in the space U. Okay, so our formulation, I will suppose that U can be identified as a product of two spaces through an isomorphism, okay? And then associated to B, I have two operators, B1 and B2, okay? So I have this relation between B and B1 and B2. So I can written my control problem as a switching control problem, called SCP, okay? Where now we have two controls here, U1 and U2, okay? So our goal is try to construct switching controls that is controls U1 and U2 such that at almost time t in the interval 0t, this product is 0. Informally, this means that only one control is active at each time. So here I have two controls, but at any time, only one control is acting on the system. Okay, I'm interested to answer this question. If it is possible to construct control that two controls that are not acting at the same time. Okay, so this is what we call switching control. Okay, so one hypothesis that we should assume is that with two controls, the system is controllable. Because if with two controls, the system is not controllable, there is no sense to talk about switching controls, okay? So a typical assumption that we should suppose is that the control problem, CP, is non-controllable in arbitrary small times. Okay, and this, as we see before, is equivalent to an observability inequality for the system, for the adjoint system. Okay, so we go a little bit fast here. So here is two kind of example in which we have switching control. It is adaptive cruise control in your car. So when we want to, the accelerator and the brake, when we want to keep the velocity of our car, since the road is irregular, so we should switching between the accelerate and the brake, okay? And the another example is the traffic light. Here is New York, in which you have plenty of traffic light, and this is more or less enough to control the traffic. And this is a picture in India, where there is no traffic light, and I think that it's a little bit complicated to drive there. Okay, so previous work here. We are strongly inspired in this work by Enrique Zuazua, switching controls in the journal European Mathematical Society. And here he considered only the finite dimensional case, and under this strong assumption, okay? And that are another works by the group of Karl Kunisch at the University of Graz. Okay, so our main result is this one. This is our theorem, in which we consider B as a bounded operator and A is a self-adjoint positive definite operator with compact resolvent. Okay, and we are in the framework of Hilbert space. Okay, so if we have these two hypotheses, then and the system is null controllable at arbitrary small times, then our system is null controllable with switching controls. Okay, so the idea of the proof. So we just recall some previous formulation. Okay, so we see that the control problem is null controllable if only if the adjoint problem is weakly observable. Okay, and that is a classical way to construct the control in this case, because this just proves that the problem is controllable, but do not give us the way to construct it. So the typical way is consider a functional and minimize this functional. Okay, so the minimum of proof that this functional has a minimum, and then use the Euler-Lagrange equation associated to this function. So we compute the Gateau derivative of this function, and the Gateau derivative of this function give us a formula for the control. Okay, and this is exactly the concept of weak solution for this CP problem. Okay, so this was the motivation of Souza in order to construct switching control in the finite dimensional case. So he considered this another function in which he replaced the square norm here by this maximum. Okay, so if we assume that the observability inequality, the system is null controllable with any controls, with two controls, and we use the equivalence between all the norm in the finite dimension framework, we see that the weak observability implies to this switching observability inequality. Let's call it like that. And this switching observability inequality is enough to prove the coercivity of this functional, and the coercivity of this functional plus some hypothesis implies that the existence of a minimizer for this function. And okay, we want to write the Euler-Lagrange equations. So in order to characterize the control, so the key point is analyze this set. Okay, is the set where these two quantities are equal. Then if we assume that this set is of zero measure, so then we can compute the Euler-Lagrange equations. So assuming that hypothesis, the Euler-Lagrange equation satisfies this hypothesis, satisfies this identity, where I1 and Y2 are given by that. And then this given exactly a formulation and is special for the switching control. Here you have U1, which is given by that at the set I1, and U2 is given by that at the set I2. Okay, and these two controllers are switching. Okay, so the conclusion is that the main difficult part is see some hypotheses which ensure that this I1 set is of zero measure. So our approach, we introduce a parameter, a functional analytic function alpha t here in the functional. Okay. For instance, we can take this one. Okay. And the goal is to guarantee that this set is of measure 0. Okay, so we will use the analyticity of the semigroup and some spectral property of the operator in order to see that this set is of 0 measure. So, okay, so since our operator generates a semigroup, it's a little bit classical here that if I define F by this, since alpha is analytic and Z is analytic in this set, so this function F is analytic in this set, minus infinity to capital T. Then if I is positive, which means that if F of F is equal to 0 in I, then thanks to the analyticity of F, we have that F is identically to 0 in this set. So the goal is to prove that F is cannot be 0, okay, except in the case where B star Z and B2 star Z are equal to 0. If this happens, so we can use the unicontinuation property and guarantee that Z of T is equal to 0. And these do not give us a switching control. Okay, so if we prove that, then we guarantee that that set is of 0 measure. Okay, so thanks to this hypothesis that we consider for the operator A, okay, we can decompose our operator in some spectral form. Okay, so we decompose the initial condition in this form, and the solution is given. The analytic solution, analytic in T, is given by this. Okay, so in order to prove that this cannot happen, we will consider, we will prove by contradiction. We consider K naught the infimum of the case such that this is not 0, and the goal is to prove that this K naught is infinity. This K naught cannot be finite, which means that B1 star of the basis of the space H are equal to 0 for every K. Okay, so if K naught is finite, then I'm not finished. Okay, so we have that this is not 0 for K naught. Okay, so we can write Z like that plus some residuum. Okay, where ZR is like that. So we assume that F is identical to 0 in this set. Then we can rewrite this expression for F like that. And then we can we can take the limit here, and these two guys vanish. Okay. But since, because the eigenvalues are increasing to infinity, okay? And using the properties of alpha, since alpha is 1 plus 1 over 2 sine of WT, we have that this is equal to 0 for any alpha infinity between these two quantities. So this is a linear combination of two guys. So this means that these two guys are 0, but this is a contradiction because we assume that K naught is finite, and which means that at K naught, these two quantities are not zero. So, and we obtain that these two quantities are zero. So this is a contradiction. K naught is infinity, which implies that B1 Z is equal to zero and B2 Z is equal to zero. And this, by the unit continuation property, imply that ZT is equal to zero. Okay, so this theorem can be generalized into considering any controls. Okay, and the switching control properties is like that. Okay, and there is an application in the case of Stokes. So if anyone is interested, can ask in the question turn. And as a conclusion, I would just finish by saying that, okay, our result also cover the finite dimensional case, which generalized the paper of Zuazua, because we do not assume any Kalman condition. Also, we treat the non-self-adjoint operator, which generate analytic semigroups. And but we need to assume very strong spectral properties. And we also cover boundary control, source term, approximate controllability with switching controls. And a question is that since we use some spectral properties of our operator, our method cannot be applied to the time-dependent operator with time-dependent coefficient. So this is all. Thank you very much for your attention.